Good afternoon. This is Kyle Welch with RCR Wireless News. Thank you for attending Antenna Evolution, meeting the demand for LTE Small Cell and DAS networks, presented by Galtronics. Our presenter today is David C. Wittwer, Principal RF Engineer at Galtronics USA. At this time, I'd like to hand the presentation over to David.
Okay, thanks, Kyle. And thanks to everyone for joining the webinar today and taking the time to understand a little bit more about the role antennas play in the LTE DAS and small cell networks. During the presentation today, I'd like to cover a few major topics. First, to set the groundwork for the presentation, I want to review macro, DAS, and small cells and what the attributes are of each of them and how they differ. Next, I want to discuss antenna fundamentals, and the reason for repeating this information that may be so familiar to many of you is that I want to provide a common foundation for discussions about topics later in the presentation. Specifically, when we look at vendor data sheets, I want to make sure that we all understand the terms that are presented on those data sheets and how they'll impact your project designs as well as antenna selection. Following that, I want to discuss a little bit the importance of gain and directivity on the coverage in your projects, and then discuss mounting options that are available to you when you're designing these projects and installing antennas in different kinds of venues. Finally, the selection of antennas and how they may impact your ability to capitalize on the maximum MIMO capacity possible. I'll finish up the presentation with a few comments on passive intermodulation and then conclude with a summary. So let's get started. Traditionally, network coverage has been based on sort of macro network deployments where we have a centralized base station unit that provides capacity to a single sector. Now, in this case, the capacity comes from the base station, which is a very large piece of equipment mounted inside of an environmental enclosure at the base of a tower. That concept has been repeated as we move into DAS systems where the same base station is now located in an enclosure in, say, a parking structure inside of a casino or a hotel. When we move to small cells, we actually break from this centralized capacity concept where the capacity is now provided by the small cell itself, not a particular base station unit, and that small cell provides Ethernet or fiber backhaul or backhaul over a set dedicated radio channel with the macro network. So in this sense, small cells represents a new category of coverage solutions which may be deployed in the field. If we next look at bandwidth, macro antennas historically have been very narrow band, meaning that for every carrier on a tower, they would have a dedicated antenna. Now, there have been evolutions in macro antenna designs that are now enabling 2, 3, 4, 5 different bands, but for the purposes of this presentation, we leave multi-band macro antennas out of the discussion. When we look at DAS systems and these DAS antennas installed inside of buildings or on light posts or telephone poles, each one of these DAS systems tends to be very broadband because most of these installations are owned and operated by neutral hosts, and the intent of the neutral host is to enable as many carriers as possible. When we look at now small cells, we're seeing at least initially that the bandwidth is quite limited for small cells, having only a single radio inside and supporting only a single carrier at a time. However, we do see plans for broadband small cells in the future. This is important to highlight at this point because installation of narrowband antennas to enable the small cells may require you to come back at a later date when you upgrade the broadband to a broadband small cell solution and have to change the antennas. This is particularly important in municipalities that have strict zoning restrictions, and when you consider the number of small cells that plan to be deployed throughout the United States in the coming years, the amount of paperwork involved in obtaining licenses and zoning approvals poses a fairly significant challenge. The idea here is that we need to understand that in the future broadband small cells will be enabled so that broadband antennas may be employed early on so we can limit the amount of zoning and planning that needs to happen. We don't want to have to go back later and acquire new licenses and new zoning approvals when we upgrade to a broadband solution. So just something to keep in mind. Other differences between macro are in terms of how high the antennas are actually installed. So for macro networks, we see antennas installed, much greater than 30 feet. These are mounted on top of towers. They're mounted on the sides of multi-story buildings. They're very far from the user. And as a consequence, you're able to install quite large antennas on the order of 5 to 10 feet in length that give very good performance. When you look at DAS installations, we now have these radiators installed within a few feet of the user or at heights of around 8 to 10 feet for indoors, or on utility poles of less than 35 feet. So the antenna is much closer to the user, and the acceptable size of the antenna from a visual impact standpoint is on the order of less than a foot for indoor or less than 4 feet for outdoor, and the 4-foot restriction is coming from the desire to locate these antennas inside of the comm zone, which is actually below the telephone wires. When we look at small cells, they have similar requirements on mounting the antennas very close to the user. Again, 8 to 10 feet for indoor applications and 10 to 20 feet for outdoor applications. Because of the close proximity to the user, the same dimensional requirements still exist for these antennas, namely less than a foot for indoor antennas and less than 4 feet for outdoor antennas. And some further information about differences for macro, DAS and small cell is macro antennas or macro installations typically have one antenna per sector. Again, this presentation is not comprehending concepts like split cell macro antennas and things like that. There are advances in the macro antenna space, but for comparison purposes, we're ignoring those. So macros have one antenna per sector. When you look at a DAS, you may have one sector of the base station connected to as many as 12 antennas distributed throughout a floor. So this is significant in that you may have 4, 5, 6 antennas on a single sector, and because they're on that sector, the definition between coverage from one antenna and the next isn't so significant because all of those antennas are on a single sector. You do still have to be concerned with sector boundaries where you have a group of DAS antennas that now come in close proximity to the next group of DAS antennas. This is a so-called sector boundary, so you still have those concerns there, but it's not with every antenna as it would be in the case for macro. And now when we look at small cells, we'll see that we have 2 antennas per sector, and each small cell in fact represents or can be thought of as its own sector. So the 2 antennas here would be for a main or a diversity antenna and a 3G small cell application, or a MIMO path A and a MIMO path B antenna in LTE MIMO configuration. And again, because the small cells can be considered as their own sector, we need to be very concerned about controlling the coverage and making sure we manage these cell edge and hard handover regions in space. And finally, one of the most significant differences between macro, DAS, and small cells is the power output of these systems. With macros outputting 40 or more watts per sector, which is a considerable amount of power, in comparison to DAS systems, which are 10 to 20 watts. And the number here is just in comparison. There are many different types of DAS. Passive DAS will obviously output a lot more power than an active or fiber-fed DAS. So we're just simply providing an order of magnitude difference for comparison here between macros. And then finally, when we look at small cells, we see that the output power for indoor small cells is on the order of 1 watt, and for outdoor small cells, we see up to 5 watts of transmit power, which is 10 times less than we would see in terms of a macro. So taking all of this information into mind, the one takeaway I'd like everyone to remember after this presentation is that DAS and small cell antennas are installed much closer to the user. They're required to be much smaller, and they have very broad bandwidths. Okay, so let's establish some common language, and this is important when we look at data sheets for antennas. It's important to realize that an antenna is a one-port linear passive device. The things that we can measure and quantify about an antenna are how much power is actually reflected back and from the antenna, and that tells us ultimately in an indirect way how much power is accepted by the antenna. And then the next thing that we can measure is how much power is actually radiated from the antenna. And obviously the ratio of the radiated power to the accepted power is an antenna efficiency. That's a very important quantity. Unfortunately, we don't see that on data sheets for macro or even DAS and small cell antennas. But what it tells us is how lossy the antenna is. Typically in directive antennas, like the outdoor macro antennas, the loss in the system is not particularly critical, or it's not as critical as directivity is, or what is the beam width of the antenna and the elevation in the azimuth plane. So the metric that we use to measure how much power is reflected is called return loss. Tends to be numbers that are difficult to deal with, and engineers like to keep things simple, so we have another quantity called VSWR, which is easier to remember. The numbers are like 1.5 to 1, 1.7 to 1, things like that. But it's an indication of how much power the antenna accepts. And then because the antenna radiates power in all directions, the directivity of the antenna is important, but it's a distribution of numbers, right? It's a measure of the antenna's preference to radiate power in a given direction. And that's very difficult to represent on a data sheet. So gain is typically used, but gain is only a representation of the highest directivity value, or the maximum of the directivity, times the efficiency. And it's important to remember that when we talk about antenna gain, it's not like amplifier gain. We're not comparing the output of the system with the input of the system. We're comparing the peak of the antenna directivity for our desired antenna with an idealized antenna or an isotropic antenna. So it's important to remember that that I in the subscript for dB, it's important. It's not dBm, it's I. The antenna doesn't add power to the system. So moving on, we can look at VSWR and how it relates to how much power is accepted to the antenna. This is just a simple graph that shows VSWR along the x-axis, and we can pick a few values off here that you will see on data sheets. VSWR of 2 to 1 represents 89% of the power actually transmitted to the antenna or accepted by the antenna. And you can see as you change that spec value from 2 to 1 to 1.7 to 1 to 1.5 to 1, that you're speccing that more power be accepted by the antenna. So from 89% to 93 to 96%. So the point here is that whatever spec or limit is established by your project installation or the carrier that you're doing that installation for, they will pick an accepted power level for the antenna, and then they will design the system around that. So just still just background and establishing a common language here. So let's take that common language and look at a data sheet and see where this information is represented. So obviously the VSWR, which we just talked about, is shown on most data sheets. Typical values of 1.71 are pretty good, and more challenging, higher standard installations, you'll be required to meet a 1.5 to 1 type VSWR. Again, the difference there being only 3% difference in the accepted input power of the antenna. And then the next most important thing that people tend to focus on, anytime you say the word antenna, people say gain. And this is something that, yes, is important, but it needs to be taken at the same time as you also understand what the directivity or the shape of the pattern is. So focusing on gain for a moment, you can see on this data sheet that the gain is broken out by frequency, You'll also note that as you move up in frequency, that the gain becomes higher, and this is because the antenna becomes physically larger and creates more directivity in the pattern, meaning that the antenna starts to have more of a preference to radiate in a given direction. One thing that's you want to be careful of is that sometimes antenna vendors will represent the gain of their antenna as a single number for all frequencies, in which case folks might choose the highest gain, which in this case would be up at 6 gigahertz. So you need to be aware of what the gain of the antenna is for your operating frequency, and if the datasheet you're looking at doesn't call out specifically what the gain is for your frequency, you might want to ask the supplier to provide you that information so that you have an accurate picture of what the antenna is doing where you're operating at. And then finally at the bottom of the page is the shape of the antenna pattern. This is, in my opinion, this is the single most important aspect of choosing an antenna. The antenna's job is to provide power where you want to provide capacity. So if you're designing a broadcast system like in-building DAS or in-building small cells, you want to not have a preference for any particular direction. You want to serve all users equally well or fairly. So in that case, you want to choose an omni antenna in the azimuth plane, and you don't want to see a lot of ripple or variation in that plane. You also want the power to be directed in the general direction of the user. In this case, these antennas are installed in ceilings, and here we're showing the pattern at 19, in the high band, 1900, 2300, and to some degree even in the lower frequencies where the antenna is designed in such a way that the power is radiated below the ceiling where the users are. So on the previous slide, we discussed the importance of gain, but not only gain, but also the shape of the pattern or the distribution of the pattern in space. So we oftentimes receive questions about customers evaluating our antennas versus other antennas, and we'll hear the comment that, well, the other antenna has a higher gain. And in that scenario, it may be true that the other antenna has a higher gain, but based on the fundamentals that we just reviewed, we now know that higher gain means a preference for radiation in a given direction. If you're designing in-building applications where coverage is important to you, that preference for a given direction may not be what you're after for a coverage perspective. So what this slide simply tries to show is if you look at an omni antenna as shown on the left and what the expected coverage might be in any of your site planning tools, in this case we used IBWave, this antenna would have a lower gain than the one on the right, but the antenna pattern is more uniform, and as a result the coverage area is more uniform. So here's an example where the highest gain antenna may not provide you the best coverage, and that's the point we're trying to make with the last several slides. So what can we do, right? So if peak gain is not the only critical metric for antennas, then what else can be changed? So the directivity of the antenna, as we already highlighted, is very important to coverage. So if you all were antenna designers, what would you try to do to improve that coverage? So the things that that we thought of and that we've designed our antennas for are omni coverage in the azimuth plane, but we also want to radiate the power down below the ceiling. So in this case, you see the antenna pattern shown in the figure on the right has a gain of 6 dBi at this particular frequency, which I believe is around 1900 megahertz. We want the power, the user is located below the ceiling, right, standing on presumably a hard floor surface, typically concrete, with a reflection coefficient of something like 20%. And we want to radiate the power below the ceiling towards the user, but we also expect in building environments to see multipath reflections, which contribute power also to the received signal. So an antenna pattern like this is something that we believe is beneficial for in-building installations because it provides more power where the users are, and in addition to that, it doesn't radiate power up into the plenum space above the ceiling. And in that space, you know, there are several presentations available from folks more qualified than I am to talk about PIM, where PIM sources that may exist in the plenum space, you know, won't be excited if you don't radiate power in their direction. So this pattern shape that's been we've been designing to, we've called pair, and the term pair comes from if you look at this pattern shape versus a dipole, if you look at the cross section of a dipole, it looks like an apple. If you look at the cross section of what we're designing for, it looks more pear shaped, where the bottom lobes receive more power. Okay, so three things: we're radiating power below the ceiling, we're trying to stimulate multipath environment, we're trying to stimulate that multipath environment because that is required to give high order modulation, high order capacity in MIMO systems. And then finally, we're trying not to excite external PIM sources to the antenna, which may be located in the plenum space. There are some references here at the bottom of the page. If you're interested, contact me and I'll put you in touch with these folks that are very knowledgeable in these areas. Okay, so now we have the ability, now I want to talk a little bit about selection of the antenna and where to place the antenna. A lot of venues are very critical about the appearance of any installation of technical equipment in their beautiful buildings. So the placement of antennas below ceilings is not always an option. So it becomes significantly important to be able to offer options of where to place the antenna. And in this scenario here, we've actually provided a through ceiling and an above ceiling mounting option that allows you to reduce the visual impact of the antenna or eliminate the visual impact of the antenna. Now, we oftentimes get questions about, well, if you install the antenna above the ceiling, what is the impact on the antenna performance? So we have conducted studies where we've actually measured the antenna in a free space scenario, and then we've included the through ceiling mounting bracket, a section of ceiling tile, and the mounting frame that generally holds suspended ceilings, and repeated the test. And then we've also included that section, the above ceiling mounting kit, and the ceiling tile section and frame as well. Now, keep in mind in these pictures that because we're in an antenna chamber and our coordinate system is inverted from how these antennas would be installed in the field, that's why things may look upside down to you. If we go on to the next slide, this is a comparison of those measurements. And in this case, we see at 820 megahertz, when we look at the pattern below the ceiling, we have a gain. Again, this is directivity times efficiency. We have gain of around 2. When we do the through ceiling mounting, we have a gain of around 1.93. So at this particular frequency, the antenna pattern shape has not changed that much, and the antenna efficiency has not changed that much. And then when we move the antenna above the ceiling tile, the gain actually goes up, and this is a result of reduced efficiency that is more than compensated for by increased directivity. And how do we know the directivity is increased? Because the shape of the pattern is increased. It's not as dramatic in this case as it will be on the next slide where we look at 1900 megahertz, but the shape is canged. So you see, by creating this antenna pattern where we direct the energy below the ceiling, below the plane of the ceiling, we're able to now install the antenna through and above the ceiling without impacting the antenna performance significantly. So if we look at the same scenario for the 1900 megahertz case, we see that we have a gain of 6.5 or 6.4 for the below ceiling case. For the through ceiling case, it's 5.5 dB. And again, you can start to see the change in the pattern shape. And then as you go above the ceiling with the antenna, the gain is 6.2. If we look at a comparison across frequency of the reduction in antenna efficiency, right? We've seen from the previous slides that the gain goes up, but what's plotted here is the reduction in efficiency by mounting the antenna through the ceiling or mounting the antenna above the ceiling. We see that we only experience about a 3% reduction in the low frequency bands and less than an 8% reduction in the high frequency bands, but the gain still remains high. Even though the efficiency goes down, the directivity goes up to compensate, and it goes up more than the efficiency goes down. So, you know, the net that we want you to remember after the webinar today is that using a pear-shaped antenna pattern allows you to mount through and above the ceiling. This can be extremely useful when you're working in sensitive venues where they don't want to see the antennas, and you can be confident that doing that doesn't impact the performance of the antenna. Okay, so what other things do we need to be concerned about when installing antennas for MIMO systems? So several years ago, the carriers spent billions of dollars purchasing spectrum, and their intent was to roll out LTE, and we're starting to see that now. And the promise of LTE is increased capacity and throughput. So what we do on the installation of the antenna side needs to make sure that that full potential is realized. So how do we, what options do we have for installing MIMO antennas? Well, the simple approach is you just install 2 vertically polarized antennas and separate them by a suitable distance, which probably is around 6 feet, and you can get MIMO capacities in that case. But the downside of that is now, from an installation standpoint, I have to make have an extra length of cable to get to that 6-foot distance, and I have to punch 2 holes in the ceiling. So there's a little bit extra installation cost, labor, and time. In contrast to that, if we look at co-located dual polarized antenna solutions, in this case we have 2 antennas still, but they're located in a single enclosure. It means we're punching 1 hole in the ceiling and we're running our cable runs to 1 location. And the antennas operate in a cross-polarized fashion so they don't interact with one another. And we want to see, is this a viable option or a viable solution? So we did some testing in Las Vegas. If you're familiar with Galtronics, you've likely heard or seen the results. But what I want to briefly discuss here is that when you use cross-polarized co-located antennas, you're actually able to achieve a little bit higher throughput than you would be if you just use 2 spatially separated vertically polarized antennas. So again, it's back to this question of the carrier spent a bunch of money on this spectrum in an effort to realize the highest capacity possible. From an antenna perspective, we don't want to be the limiting factor. So if you want to achieve the highest capacity possible, you're more likely than not going to be able to achieve that through the use of co-located cross-polarized antennas. So this is a study that Galtronics performed. As back, I think the study was done in 2012, and we published the white paper in 2013. If you're interested in that white paper, contact us. We'll be more than happy to provide it to you. More importantly than what we've done is that there have been, I think about 6 months after we published our paper, there was an independent verification by, I think it was a TELUS lab in South Africa that basically recreated exactly the same kind of testing and came to the same conclusions. If you're interested in that reference, also contact us and we'll dig it up and forward it on to you. Okay, so another aspect that we get asked about is when doing installations of MIMO antennas, does the gain of the MIMO path A antenna need to be exactly the same as the MIMO path B antenna? And this is something that we wanted to quantify and try to understand better even for ourselves. And I think you might find the result to be a bit surprising. First of all, this is a theoretical analysis. It's based on a MIMO system model. And in this system model, the gain of MIMO path A antenna and MIMO path B antenna are included, and this allows us to look at changes in the channel condition number or the channel rank based on gain imbalances, meaning that gain of MIMO path A is different than the gain of MIMO path B. So what's shown in this graph is for a particular channel instance, the x-axis represents the gain imbalance, the delta gain between MIMO path A and MIMO path B. The y-axis indicates the channel, in this case it's the condition number of the matrix, which relates to how invertible the matrix is, and it's plotted on a log scale. So you can see that gain imbalances of 3 to 5 dB, surprisingly enough, only result in a change of the channel condition number of 1 dB. So despite our best efforts, the laws of physics seem to be in our favor here. So the MIMO system itself seems to be tolerant to these gain imbalances of the antenna. Now, don't take this the wrong way. By no means am I recommending that you go out and install antennas with different gains, but if they're different by 1 or 2 dB, I wouldn't expect that to impact the quality of the installation at all, just based on this study. Again, we've written an internal white paper on that. If you're interested in the details, contact us. I'd be more than happy to share that with you and discuss it with you. Okay, so finally we arrive at discussion about PIM. I think as most people on the call are probably very aware, PIM is it's a nonlinear effect. It comes about by the excitation of some nonlinear junction in either a component or in the space surrounding the radiator. And what's shown here is that if you look at the diode equation, the exponential term can be replaced by a Taylor series expansion, in which case you start to see the squared terms. And if you remember your trigonometry identities, squares of cosines generate plus and minus angle products there and create this spectrum that's non-ideal. So that's the math bit at the top, and the figure at the right shows a practical measurement of it. This is just something from the internet, but you see 2 tones, and then on the scope there you see the noise floor, and then you see the intermodulation products popping up above the noise floor. Now this is important because the noise floor is significant, and the amplitude of those peaks relative to the noise floor is significant. Obviously, if those peaks were below the noise floor, then the intermodulation wouldn't be so much of an issue. What I want to limit the discussion to today is self-generated PIM, meaning PIM created by the antenna element. We still continue to recommend that you use PIM compliant and PIM certified antenna components because it's a quality assurance measure. It means that there's not been an error in the soldering process or the assembly process of the antenna. And we also want to provide some confidence that when you install these antennas in your systems, that the antenna element itself is not generating PIM, and that you don't need to investigate that as a potential source. This is in contrast to external PIM source. And again, there are folks on the call that are more adept at discussing this than I am, but it's potential, there is a potential for the antenna to excite nonlinear junctions in the environment, which can come back in and impact your noise floor and ultimately reduce capacity and all the other bad stuff that happens with PIM. We're not addressing that per se in this presentation. However, if you'd like to discuss that, again, contact us. We'd be happy to talk about it. So as was shown on the graph, or the photo on the previous slide, the noise floor is fairly significant when talking about PIM, and where is the noise floor relative to the PIM source. So if we recall, the noise floor of any receiver is determined by the filter bandwidth at the input. So what I've shown here is just the filter bandwidth from the 3GPP for LTE systems. So 1.435 and 20 megahertz bandwidths. We can see that the noise floor defined, the thermal noise floor defined by those filter bandwidths corresponds to neg113 up to neg101. This is something different if you're used to working in 3G systems. The 3G system channel bandwidths there are significantly narrower, and because they're narrower, you end up with much lower noise floors. So LTE channel bandwidths here definitely increase the noise floor, and we need to keep that in mind. And then the thing that I want to conclude with here on PIM is when we look at the dynamic range of a system, right? Let's talk about that. The dynamic range of the system would be the difference between how much power is radiated, or the total EIRP from the transmitter, the difference between that and our ability to, the smallest signal that we're able to receive. Well, it turns out the smallest signal we're able to receive is determined by the noise floor level, which again is proportional to the channel bandwidth, and also the noise figure of the receiver. Now, so in this case, we talk about a macro type installation where we're transmitting 40 watts or plus 46 dBm for a 20 megahertz channel. The noise floor is at minus 101 dBm, and let's assume a 10 dB noise figure. And as an antenna guy, I have no idea if that reflects a valid noise figure for a receiver for a particular equipment. These numbers are simply illustrative. But what we see here is that the difference between the transmit power and the smallest signal that we're actually able to receive is 137 dBm. So, what that means that as long as we don't have PIM sources that are higher than minus 130 dBc, we should not expect to see any kind of impact on our transmit and receive signal from PIM. So let's look at some variations in these numbers. So the table at the top represents a 6 dB noise figure, which is a pretty good noise figure for a receiver, versus filter bandwidth for the input and transmit equivalent power across the top. Okay, so when you look at 40 dB transmit power, which is again something similar to what you might see in macro networks, and you look at very narrow bandwidths, 1.4 megahertz, you see that you can easily get down to a dynamic range of 153 dBc. So this is what's traditionally driven the PIM requirement for 150 dBc on all passive components in a macro and DAS and small cell system. However, as you start to increase the channel bandwidth, which is the case, I think most carriers are probably deploying 5 or 10 megahertz LTE channel bandwidths, and you assume a 6 dB noise figure, which is still pretty good, you start moving away from, or you start reducing the dynamic range of the system, and the necessity of a 153 dBc PIM requirement goes away. What's included here, the red line is something that exceeds the 150 mark. If you add a 10 dB margin just to be safe, so 140 dB, I would still be concerned and still want to be using PIM certified, PIM compliant products. But as you go down in the power levels, at the very beginning we said 40 dB or 40 watts represents macro, 10 and 20 watts probably represent DAS systems, and then 5 watts are outdoor small cells and 1 watt are indoor small cells. So we see for indoor small cells, the dynamic range of the system is considerably smaller, and we wouldn't expect to see self-generated PIM be an issue if we use minus 150 dBc certified components. Now, the table at the bottom of the slides here is essentially the same information, but we've increased the noise figure of the receiver. I've heard estimates for this to be as high as 20 and maybe even 40 dB, but the trend here is that as the noise figure is increased of the receiver, the ability to see these intermodulation products caused by self-generated PIM, not external PIM. You see that increase in noise figure actually reduces the dynamic range and maybe even your ability to see those PIM sources. So again, caveat at the bottom, the noise figure numbers here are just illustrative and they don't reflect a particular product's performance. We're just trying to show the relationship between noise floor, filter bandwidth, and noise figure and what's important. But since we're using low power radios for small cells, we don't expect self-generated PIM to be an issue, provided the components used meet the minus 150 dBc requirement. So summary, just to follow up here, so DAS and small cell antennas are installed much closer to the user. That means they need to be physically smaller, but at the same time they need to accommodate more and more bandwidth. That has an impact on VSWR and also the shape of the antenna patterns. They'll have larger beam widths. Next, the antenna patterns are at least as important as antenna gain. So when you're looking at data sheets and you're choosing a particular antenna for your project or application, the shape of the pattern should be your primary concern, and then the gain of the antenna maybe should be considered second. Also, for your project, mounting options may be very important to you. You should know that mounting the antenna above or through the ceiling doesn't result in any significant impact to the antenna performance, but may aid you in getting building owner approval. Next, when possible, choose cross-polarized co-located antennas to provide, number one, to provide increased capacity, right? To provide the most value for the carrier spectrum, and then for a second reason, just to reduce the installation cost. And then the final conclusion from today's seminar that I'd like you to think about is the lower power for small cells that are deployed with, well, I should say LTE small cells, not 3G small cells, but the LTE broadband signals small cells have a modest noise figure, so we don't expect those to be significant generators, self-generators of PIM. And in those cases where you're concerned with the excitation of external PIM, the use of pear-shaped antenna patterns versus apple-shaped antenna patterns can be useful to stop from exciting those external PIM sources. So again, thank you all for taking the time out of your busy schedules today for joining the webinar. Kyle, I'd be happy to take questions, and thanks y'all for your time.
All right, thanks, David. Yeah, we've had quite a few questions come in, so we'll just get through as many as we can. So the first one is, in what cases is DBD applicable instead of DBI?
DBD is it's just a preference, and it's whether you choose to compare your antenna under test with a dipole or an isotropic radiator. And the conversion between the two is relatively simple. It's just a factor of 2.1. As a standard practice, over the last 30 years, I think people probably use DBI more than use DBD. Although in the ham radio space, I think people tend to continue to use DBD. It's a matter of preference. It's what you choose to compare against.
Great. Next question, what is the antenna efficiency for Galtronics indoor and outdoor antennas?
So the antenna efficiency for our indoor antennas tends to be very high, up in the 80 to 85%. We can be happy to follow up with that with the actual graphs and the data. And then for the outdoor outdoor DAS antennas, I'm not sure that we've actually even looked at the data because, again, in those scenarios, it's more of a point-to-point or point-to-multipoint application, and we're more concerned with controlling the radiation within a particular sector, meaning maintaining the 3 dB beam width of 60 degrees or 90 degrees and the elevation beam width of 12 degrees or so. Certainly that information is available and we can provide it. We'll follow up after the webinar.
Great. Next question, what is the minimum port-to-port isolation for MIMO antennas?
Okay, so port-to-port isolation, to answer that question, we need to really kind of have an understanding of how MIMO works. So MIMO transmits two messages over the same frequency at the same time, and the ability to unmodulate those signals or separate those signals back out at the receiver involves the inversion of a matrix. So the port-to-port isolation on the antennas only needs to be different from, well, let me back up. I can answer it and say 12 to 15 dB in the low band is typical and 20 dB is achievable. The more isolation you have, the easier it is to invert the matrix. But in reality, I don't believe you need, and we have simulation models to back this up, I don't believe you need more than 15 dB isolation to be able to invert those matrices and get the capacity. I hope that answers the question. If not, contact me and we can discuss more.
Great. Next one. How is antenna VSWR affected by different mounting options?
There is some impact, but again, if you recall the slide that was where we plotted VSWR versus accepted power by the antenna. So when you mount, maybe the question was about is the VSWR of the antenna impacted when you mount below, through, or above? In that case, we're able to show that we still meet the requirements on the datasheet. So if we spec 1.701 in the high band, we will meet 1.701 in the below, through, or above configuration. If the question was about if I mount the antenna in a scenario and the VSWR is degraded, what's the impact? If that was the question, then this graph should help answer that question. So if it's a 1.701 antenna, it means I have 93% power transfer, but when I mount it in a particular configuration and say the VSWR drops to 2.2, in that case I'll drop down to an 80% power accepted by the antenna, or it means I've reduced by 3% the amount of power that makes it into the antenna.
Okay, great. Next, for indoor environments, operators usually do not share the DAS with Wi-Fi. Does Galtronics offer a Wi-Fi antenna solution for multi-stream MIMO?
All of our DAS antennas, I should say all of our in-building DAS antennas support up to 6 gigahertz. And the reason for that is that we wanted to make it possible for sharing of DAS with cellular and Wi-Fi networks. We didn't know if that was going to be the case, but we didn't want our antenna solutions to be limited by that should the market choose to go in that direction. So if you're looking to have a cellular and a Wi-Fi network shared on the same antenna, certainly you can do it on the existing product line. If you're looking for in-building Wi-Fi antenna only and you're not interested in the cellular side, you might want to choose other antennas that we have for that would be physically smaller, easier to conceal, more aesthetically pleasing.
And I guess to kind of go along with that, could you explain a little further about how Galtronics antennas take advantage of multipath signals?
Yeah, so we made the comment earlier that our antenna patterns are directed towards below the ceiling, And we're actually relying on that bounce off of the concrete floor or whatever structure is below. The presence of multipath is required to be able to separate those two transmitted signals in a 2x2 MIMO system. So you can imagine, without multipath, I'm not able to achieve my, 54 megabits per second or whatever 100 megabits per second that are available. And that's because the two messages are correlated, and when they're correlated, I'm not actually able to separate the information well. Now, when I have decorrelation between the signals, I'm more able to separate those signals, and the way that you get decorrelation is through the introduction of multipath. So if I just had a dipole pattern antenna and I'm radiating most of my power in the horizontal plane, the multipath reflection is actually reduced by the angle below the ceiling, right? So if we look at this slide with my little cartoon of the stick man, the blue or teal colored ray to the user is the multipath bounce. And you can see that our antennas have peak gains in this direction. So this is one of the ways in which we try to increase the MIMO capacity of our antennas.
Great. So next question, what critical design criteria do you think need to be addressed for outdoor small cell applications?
So for outdoor small cells, we're dealing in the 5-watt range. The most critical thing here is that you put the radiated power in the desired location. So we see on the market there are a lot of small cell solutions with embedded antennas, and for a lot of applications that may be sufficient. But say, for example, you're installing on a lamp post, and when you install the small cell on the lamp post, you're probably going to want to provide coverage in two directions, say up and down the street. In that case, you might want to choose two directional antennas as external solutions to help provide radiated power where you want the coverage versus having more of an omni pattern that's probably provided by the internal antenna solutions.
Okay, great. So what do you see as the biggest obstacles for outdoor small cell applications, such as size, zoning, and price?
I'm not sure I can comment on the price. Obviously, size and zoning are going to be the biggest issues. So when you read in the news that a particular carrier is going to be rolling out, tens of thousands of small cells, the paperwork involved in that in terms of getting licenses and permitting has got to be a horrific undertaking. So keep in mind that every municipality has their own laws and regulations for what can and can't be installed. So once you go through this process, just to get your small cell mounted on a pole somewhere, that's a tremendous feat. Now, if 6 months or a year from now you decide that just that 3G installation isn't really what I want in that environment, I want to upgrade or add LTE to that small cell, I don't want to have to go back and resubmit for all my permitting and licenses again. I would like to simply do a maintenance call where I replace the box on the pole and not the antennas, and be able to add that capability. For some reason, municipalities and zoning laws are concerned about antennas more than they are just the electronic boxes. So you don't want to be having to go back and replacing the antennas later. So what that means is, install multi-band broadband antennas from the get-go, from day one, so that you don't have to reapply for permitting and licenses down the road.
Okay. We have time for one more question. As we approach increased deployment of LTE MIMO systems for both DAS and small cells, what crucial attributes of the antennas need to be considered most?
I think the biggest concern, and hopefully, if you remember one thing out of today's presentation, is it's it's control of where the power is radiated is the most important thing. So if I'm deploying a small cell DAS, I want to control where that power is, particularly for small cells where each small cell is an independent sector. So I need to be able to control my sector boundary and try to avoid these hard handoff scenarios when I get in gray areas between DAS and small cells, or when I'm outside, I don't want to be covering areas where I might be interfering with the existing macro network. So uh, control of the radiation into a confined and defined space.
Okay, that's all the time we have. I want to thank everyone for attending Antenna Evolution, meeting the demand for LTE Small Cell and DAS networks, presented by Galtronics. Again, our presenter today was David C. Wittwer, Principal RF Engineer at Galtronics USA. Thanks, David.
Thanks, everyone. Bye-bye.